Swayam Prabha. Digital India. Educated India.
Hello, welcome to Basics of Finite Element Analysis. This is the third day of the first week. In our last lecture, we had explained two important concepts. One is using this example of where we were trying to calculate the area under a complicated curve. We had explained what is meant by an interpolation function or a shape function. That is one concept we had introduced. And the second thing we had shown was that the error, at least in context of that particular example, between the exact value and the numerical value of the area under a curve depended on two parameters. One was the size of the element of size of the element. So the larger the number of elements, the lesser was the size. And then the second way to reduce error was to have a more accurate interpolation function or shape function. What we are going to do today is we will continue that discussion, but in context of a different example. So what we will do is consider the example of heat conduction. Okay. So suppose I have a hollow pipe and this is the outside diameter, outside circle. The inside circle is having a radius of r I and the outside circle has a radius of r O, and at some radius it is r. So you have a hollow pipe. So what essentially you are seeing is the cross section of the pipe, and let us look at the boundary conditions. The first boundary condition. So what is the boundary condition? Whatever are the physical boundaries of the object, whatever conditions, physical conditions are present there, that is what is referred as boundary condition. So the first boundary condition we are specifying, we know that, is that on the inside surface we have perfect insulation. At R equals Ri. Okay. So if you have perfect insulation, there is no heat either going into the, is not crossing this boundary either in outwards or inwards at R is equal to Ri. Okay. So mathematically I can express that condition as K times R dt over dr is equal to 0 at R is equal to Ri. Okay. So how does that come? I mean, for this you have to refer to some heat conduction equations. The focus in this class will not be explaining how these conditions are coming, but if we know the condition, then how do we solve the differential equation? The second condition is that at R is equal to Ro, temperature is specified. Okay. So Ro. So T, so let us say temperature is designated by letter T. So that is T at Ro is equal to T0. So, these are the two boundary conditions. There is no heat crossing the boundary on the inner surface. On the outer surface, temperature is T0. Okay. Now, we had explained earlier that if we have to solve, and the other third thing is, and that is not a boundary condition, that there is heat being generated in this whole volume of the thing. So, when you look at this problem, what you see is that the cross section of this of the pipe is axisymmetric, right? Cross section is axisymmetric. Which means there is no change in cross section if I move in the theta direction. The second thing we notice that does not matter whether I am at this position, this position, this position, this position, you know, the boundary conditions are also axisymmetric. So, whether theta is equal to 0 degrees on the outside boundary, temperature is T naught, and for any value of theta, temperature is T naught on the outside boundary. For any value of theta, there is perfect insulation on the inside boundary. So, cross section is axisymmetric, boundary conditions are axisymmetric, and then I am telling you, because we know this, that material properties are axisymmetric. An example of this would be, suppose you have a pipe, and that pipe, on that pipe I have put another pipe. Material properties are varying in the radial direction, but in the theta direction they are not varying, in the theta direction are not varying. So, this is one of those problems where material properties, this K is conductivity, K can vary in the radial direction, but it is not varying in theta direction. So, material properties are also a thing. So, if these three conditions are met, where the geometry is axisymmetric, boundary condition is axisymmetric, and material properties are axisymmetric, okay. And fourth is loading conditions are axisymmetric. So, this is the fourth condition. What do I mean by loading condition? So, it is in the volume of this pipe, in some locations heat is being generated, maybe heat is getting generated at say R is equal to RH, but it is getting generated at in an axisymmetric sort of way at a particular radius. One example could be, you have a wire, a conductor wire, copper wire, which is having several layers of insulation, right, and current is passing through it. So, wire is a source of heat, that heat is being generated in an axisymmetric way, okay. It is getting generated in an axisymmetric way. The properties of the conductivity of the wire, in the center it is that of copper, outside there is one insulation, outside of that insulation there may be another layer of insulation, there may be 3 or 4 layers. So, the material properties are changing in radial direction, but they are not changing in theta direction. Also, the cross section of the wire and all individual constants is also axisymmetric. So, everything is axisymmetric in that situation in case of wire, and same thing is here. So, if all these 4 conditions are met, cross section, boundary conditions, material properties and loading conditions, all of them you have to meet, then we can use a governing equation which neglects role of theta and z. Okay. So, z is the direction of axis and theta is the direction of angle, the hoop angle. So, we can use a governing equation which is also axisymmetric in nature. But if even one of these conditions was not axisymmetric, suppose material was not axisymmetric, then the governing equation we use cannot be of one dimensional nature. Okay. So, now I am going to write down the governing equation for this problem, because that is the first step, that we have to figure out what is the governing equation. So, we will not derive that equation in this course, we will just take it from some other book. So, for axisymmetric heat conduction problem, steady state heat conduction problem, the governing equation is 1 over R d over dr k times R dt over dr is equal to q r, and I will explain that. So, here R is radius. So, if I want to calculate the value of temperature at radius r, that is what it means. Okay. K is thermal conductivity, and this thermal conductivity does not change with theta direction, but it can change in radial direction. That is why it is in the brackets, otherwise it would have been a constant and it would have been out of the brackets. And Q is thermal load or heat generation rate, I will say. So, this is the governing equation, and we have already explained that these are the boundary conditions. So, this is the geometry, these are the boundary conditions, also heat is getting generated somewhere in the body in a axisymmetric way. So, the governing equation for this problem is this, and our aim is to find T as a function of R. Okay. So, what we are interested in finding out is how does T change as I move from Ri to R0, RO, from inside radius to outside radius. That is what my aim is. Okay. So, if you try to solve this problem using some standard way in an exact form, you will not be able to solve that problem. So, what we will do is we can solve this problem, however, using finite element method. So, now what I will do is I will just conduct first few 3-4 steps, not in detail, but at a slightly more detailed level compared to the example which we saw earlier, where we were having we were trying to calculate the area under a curve. So, the first step we do is, so what is it that we are trying to do? We are trying to calculate how is temperature, see here R is equal to Ri and here R is equal to Ro, here R is equal to Ri. How is temperature? So, temperature varying, it could vary this radially in the radial direction. So, this is, so I am trying to make a plot, x axis of the plot represents radius, y axis represents temperature. So, I am trying to get a plot of this nature, this is radius, this is temperature as a function of r, and the domain is Ri to Ro, inner radius to outer radius. Okay. My domain is, I am trying to compute the value of temperature for all values of R between Ri and Ro. So, my domain is this is Ri, this is Ro. Okay. This is my axis for radius, then this is my domain. Okay. So, the first step we do is we break this Ri to Ro, this is my domain. So, I break domain into subdomains. Subdomains. So what I am doing? I will break it up into, let us say, n elements. So this is boundary of first element, boundary of second element, boundary of third element, and so on and so forth. And this is the boundary of nth element. So this is my first element, second element, third element, and so on and so forth, and I get my nth element here. Is this clear? This is the first step. Second step. So, like in case of area, when we are trying to compute between the first boundary of the endpoint of the first element and the endpoint and the second endpoint of the first element, we assumed how that function is changing, and we could make lots of choices for those functions. In first case we said that that function was constant, in second case we said that function was linear, in third case we said function was quadratic. We have to make similar choices here. Okay. So what we do is we develop those relations. So we say that temperature in the first element, T1 means first element, at radius r is equal to, okay, T1 psi 1, and I will explain all this. So just be patient. And there is a plus T2 psi 2 r, excuse me, plus T3 1 r. What have I written? So before I explain what all this means, so I have a bunch of T's and a bunch of psi's. Okay. The superscript of T designates the element number. The superscript of T and also the superscript of psi, it designates the element number. The superscript designates the element number, because this is the terminology we will follow consistently through the course. So this is important we have to get it right. Okay. So we are trying in this equation to figure out how is temperature changing from the first point of, between the first node of element number 1 to the second node of element number 1, right? And that is why we have written T1. So this expression it tells us how is temperature changing over the first element. That's all it does. Second thing, these psi's, they also have a superscript and subscript. The superscript again for these psi's designates the element number, and they also have a subscript. These psi's are interpolation functions. And they are not any significantly different than the functions which we had considered when we were computing the area under the curve. You can assume that it is a constant function, you can assume that it is a linear function, you can assume it is a quadratic function. So this psi could be constant, and actually when we will do computation later after 4 or 5 lectures, we will actually use only these simple functions, we will not use some very complicated functions. So these are interpolation functions or shape functions. Understood? And I can have n different functions. There is no rule which says that only one function will help me explain how the shape is changing. Okay. So, I can have a constant function, and I can also add that constant function to a linear function, and I can also add that to a quadratic function, and so on and so forth, right. So, I can have n number of functions. I can have n number of functions which help us understand how the temperature is changing over the length of the element, not the overall cylinder. We are right now only at the first element. Understood? So, these are interpolation functions which help us understand how temperature is changing over the first element. They can be sine functions. What is the amplitude of a sine function? 1, right? These t's are the amplitudes of these functions. These t's are their amplitudes, and we will interpret these t's in some other way also. So, I can compress this thing as T1R is nothing but T1, instead of 1 I say J psi j R summation 1 1, and J is equal to 1 to small n. Small is the number of functions which we are considering to capture the variation of that function on an element. Okay. Big N is the number of elements. This is big N. Capital N is the number of elements. Small n is the number of functions which we are using on each specific element. Understood? Okay. Similarly, T2R, and why do I have bracket in parenthesis? Because these psi's, they are not constants, they are functions, and they are dependent on R, right. Similarly, T2R is J is equal to 1 to N T J psi j. So, you have to be patient while writing these, because there are lots of subscripts and superscripts, and the superscript will be 2. And for the nth, that is big nth element TNR, it will be summation Tj n capital N psi j n, and I am summing up over 1 to small n. Is this clear? Right. This function is valid from x0 to x0 plus h1. Let us say the h1 is the length of the first element. So, let us say this length is h1, this is h2, this is h3, and so on so forth, this is hn, big N. So, the first function is valid. After that, the element does not exist. So, we do not have to worry about that function. So, the first function will be computed only from x is equal to x0 to x. So, I am sorry, it should not be x0, it is r I to Ri plus h1. So, it is valid from Ri, which is the internal radius, to Ri plus h1, which is the length of the first element. This function is valid from Ri plus h1 to Ri plus h1 plus h2. Is this clear? And so on and so forth. So, similarly, we can find this nth t will be valid from Ro, either you add up h1 plus h2 plus hn minus 1, or from the other side it will be Ro minus hn to Ro, does not matter. Okay. So, for the eth element, so this is T1, this is T2R, this is T3R. Suppose I have to compute the value of T for eth element, then T E R is equal to T J psi j R E E n. Okay. So, I think we will close at this stage today, and we will continue this discussion tomorrow.